So our today's topic is displacement current. This is very important regarding the study of electromagnetic theory. So what is actually displacement current? To reduce or to actually have an idea about displacement current, first we need to draw a diagram. So let's say we have a capacitor like this, or it's better to take the separation a bit more. So, so let's say there is a capacitor. These are the two plates of the capacitor, and this capacitor is connected across a battery or a charging device, we can say. So this is the charging device, let's say. This is the charging device, and here we are having an AC source. The charging device is an AC whose voltage is varying with time. We know that in case of AC, voltage varies with time. So let's say this is a charging device whose EMF is given by Vt. Why? Because it is a function of time. With time, the voltage will change. Now, we know that an AC actually can go through, or capacitor allows the flow of AC through it, but not the DC. So this is the AC source, and now let's say we have, or we are considering, a circular contour like this. Sorry, like this. This contour is actually bounding two surfaces. Let's say one surface is actually like this, which is going through the separation between the parallel plates. So let's say this surface is like this. One surface is like this. This is the contour which is actually enclosing one of the plates of the capacitor and going between the separation of the plates, and the same contour is also is bounding a surface which is actually like this, which is actually bounding or enclosing the wire of this circuit, this part of the wire. So let's say this surface be S1 and this surface which is a different one, which is enclosing the separation between the two plates BS2, same contour. This same contour is actually bounding these two surfaces. Now if we want to actually apply the Ampere circuital law along this contour, then in that case, as this is an AC source, a current will actually go through. Let that current be IT. Or it's better to take green. Let that current be IT, because again it will be a function of time. With time it will vary. So this current will actually go through the whole circuit, and for the surface S1, if we actually apply the Ampere circuital law, in that case we may write that closed integral along this contour, along this contour we are taking the integral B dot dl, where B is the magnetic field at any point on the contour, is equal to mu 0 times I. That is Ampere's circuital law. This is the mathematical statement of Ampere's circuital law. Ampere's circuital law. So for S1, we must have a value for the magnetic field B, because this contour which is bounding the surface S1, it is the current I is threading through it. It is enclosing that amount of current. But if we consider the surface S2, then if we apply Ampere's circuital law again, we see that in this place closed integral B dot dl will actually give us mu 0 times this surface S2. It is actually, there is no current threading through it, because it is within the region of the plates, that is, it is in between the plates, within the separation it is actually lying. So there is no current threading through the surface S2. That means this closed integral along this contour, same contour, will actually now give us, there is no enclosed current actually, because no current is threading through it, should give us mu 0 times 0, that is 0. That is, there should not be, it suggests that there should not be any magnetic field along this contour, this dl. Dl is this. So you see, if we actually apply only the Ampere circuital law, there arises a discrepancy, because we are getting the closed integral of the magnetic field along the same contour once having some finite value and once it is suggesting it should be 0 for the same contour. So it is not possible actually. So here actually the our uh, Ampere circuital law actually fails here. So uh, what Maxwell did, Maxwell actually modified Ampere circuital law. So Maxwell actually suggested that when the capacitor is getting charged like this, the charge density of the capacitor, if we denote this by sigma, it should be Q by A, where A is the area of the capacitor. So A is area and Q, it should be written as QT, because with time the amount of charge on the plates will actually vary. So sigma should be written like this. Now what is actually the electric field? Therefore the electric field while charging within the capacitor E, again it will be a function of time because sigma is changing, it is dependent on Q. So we know that the electric field within the capacitor is given by sigma by A. That we know from Gauss's law. So this, there will be a changing electric field like this. Now if we actually want to find out the amount of current that is actually flowing, sorry, yes, the current I is, we know it is the rate of flow of charge, so it is actually dq dt. So from here we can say how we can write q in terms of E and A. Q is sigma by A, sorry this is wrong, I have written from Gauss's law, the electric field between the plates of the capacitor is given by sigma by epsilon naught, where epsilon naught is the permittivity of free space. So actually this is Q by A, because sigma is equal to Q by A epsilon naught. So from this relation we can write ddt Q as ddt of E A epsilon naught this. Now as A is constant for the plates, that is the area is constant, this can be written as epsilon naught A, or epsilon naught is constant, EA can be, this can be written as this, ddt of EA. And what is actually EA? If area is constant here, like here, is epsilon naught A dE dt. So this is actually this quantity, as you can see, epsilon naught A dE dt. This quantity is also behaving as the current, but it is not due to the flow of charge carriers. It is due to the rate of change of electric field. DEDT, changing electric field, will actually give rise to this current. This current is called actually the displacement current ID. And its expression is this, epsilon naught ADEDT. This is the displacement current. It is not due to the flow of charge. It is due to the change in electric field. So that is how actually Maxwell modified Ampere's law. He suggested that we must include this displacement current as well to actually eliminate the discrepancy that we had actually here that once it is giving same the line integral among the same contour to be some finite quantity, and once it is giving as 0. So it is not possible, and experimentally we have seen that there is actually a current existing or flowing between the plates of the capacitor when there is a change in the electric field, or rather when we apply an AC source across the capacitor. And actually we had the modified Ampere's law, which is called Ampere Maxwell's law. So Ampere Maxwell's law is given as closed integral B dot dl is equal to conduction current, sorry, mu 0 times mu 0 times conduction current plus displacement current. We have to include this displacement current in the Ampere's law. Conduction current is the current which is flowing through the wire like this, which is due to the flow of the charge carriers, and it is existing in these wires, but in the region between the plates we are having displacement current, and it is arising due to, as we have seen, the change in electric field, this one, this one. ID. So this is actually displacement current. So the amperes, this law can be written as this. Therefore, this implies closed integral d dot dl is equal to mu 0 IC plus mu 0 or mu naught epsilon naught a dE dt. So this is actually the Ampere-Maxwell law. That is how Maxwell modified Ampere's law, and it is very important, as I said, regarding the study of electromagnetic theory, because from here we can see that a changing electric field can actually produce a magnetic field. Left hand side there is a magnetic field, and how it is produced? It is produced not due to any current or conduction current, it is due to a changing electric field.